Everyone, to today's event, and it's our pleasure to invite Dr. Liu to talk about her topic. And when you have question, please post your question on the chat or raise your hand. We can take a pause and answer the question. So let's begin.
Thank you. Let me share my screen. Can you see the screen?
Yes, I can see your screen.
Okay, great. Oh. Good. Thanks for the introduction and thanks for inviting me to give a talk here. Hello, everyone. My name is Suyuan Liu. I'm currently a postdoc at Lawrence Berkeley National Lab. Today, I'm very happy to talk about my recent works on about quantum resource optimization and addressing crosstalk error. Quantum computing, wait for a moment, yeah. Quantum computing becomes more and more popular, and quantum hardware has made great progress in recent years. Like many quantum technologies have been proposed, like superconducting qubits, trapped ions, neutral atoms, and photonic chips. Even though there are many technologies to build a quantum computer, there is still no practical quantum advantage yet. The reason is because of the noise in the quantum hardware. The error rate of a quantum operation is orders of magnitude higher than the operations in the classical computers. Despite these challenges, many companies are interested in quantum computing like Google, IBM, like Amazon, etc. Almost all of these companies, they release their roadmap to say that they will produce a fault-tolerant quantum computer by 2030. So on the other hand, there are the quantum algorithms can be roughly categorized into two types. The first one is like fault-tolerant quantum algorithms. This type of algorithms usually require a huge amount of qubits, and the circuits to implement these algorithms are very deep. They are more suitable for the fault-tolerant quantum computers. Two very famous examples are Shor's algorithm and for cryptography and Grover's algorithm for the searching problem. They offer like exponential and quadratic speedup respectively. The second category is near-term quantum algorithm. This type of algorithms do not need like huge amount of qubits, and the circuits are much shallower, but they are more suitable for the near-term quantum computer. But they are just the quantum version of heuristic algorithms, and it is still not clear if they can offer the speedup compared with the classical heuristic algorithms. Examples are variational quantum eigensolver for solving the quantum chemistry problem, or we have the quantum approximate optimization algorithm for solving the combinatorial optimization algorithm. This figure shows the current situation between the quantum hardware and the applications. The x-axis is 1 over error rate, and the y-axis is the number of qubits. The current quantum hardware has around hundreds of qubits, so there is a huge gap between the current capability of the quantum hardware and the resource required by the quantum applications. Luckily, according to the quantum threshold theory, if the error rate of the quantum hardware is below a certain threshold, we can use error correction to build the gap between the hardware and the application. But to do error correction, we need the encoding and decoding process, which again require a large number of qubits, making it not that practical for the near-term quantum hardware. So what can we do more? On the hardware side, people are trying to improve the control technology to produce better qubits. And on the application side, people are trying to design better algorithms to lower down the resource requirements, but the gap is still there. So the focus of my work is to build some software tools in terms of error mitigation and circuit compilation to further close this gap. And here in this talk, I will focus on the resource optimization and addressing the crosstalk error. For the first part of this talk, I will focus on my recent work about quantum circuit resizing for resource optimization. This is the outline of this part of the talk. First, I will give a very brief introduction of some background of quantum computing to make sure that everyone is on the same page. And then I will show the motivation for resource optimization and how we achieve this by the circuit resizing with mid-circuit measurement and reset. And then I will explain the details of our proposed two resizing algorithms. And finally, I will show some experimental results and conclude. The unit of quantum information is called a qubit, and it has two properties. The first one is superposition. The state of the qubit can be represented by a linear combination of state 0 and state 1. We can visualize the qubit using block sphere. So the state of the qubit can be at any position, any location on the surface of this block sphere. And for the entanglement, when two qubits they entangle with each other, we cannot treat them independent anymore. For example, if we measure one qubit, we know the state of the other qubit as well. So here are some quantum operations for the single qubit gate. For example, we have X gate. It is like the classical NOT gate. If the input is 0, the output is 1. We also have the Hartmark gate. It is a special gate in quantum computing because it creates superposition. When the input is 0, the output is a combination of 0 and 1. In fact, all the single qubit gates can be represented using these three parameters. And this is the general formula for the single qubit gate. And all the quantum gates are unitary matrix. And by unitary matrix, I mean the U times U dagger is equal to identity. And for the two qubit gate, here's an example, the C0 gate. It creates the entanglement between the control and target qubit. When we measure the state of the qubit, we will get state 0 with probability alpha square or state 1 with probability beta square. Putting all this information together, we can create a quantum circuit. We have two qubits, each line represents a qubit. First, we apply a Hartmark gate, and then we apply a C0 gate. We measure the two qubits and store the results in the classical register. First, I want to make sure that the circuit is correct, so I use this classical simulator to simulate the circuit. So now there is no quantum involved yet. The x-axis is the output state, and the y-axis is the probabilities. We can see we can obtain state 0, 0 or 1, 1 with 1/2 probability, which is the correct results. So then we execute this circuit on IBM quantum device. We can see some unexpected results show up. These are due to the errors in the quantum hardware. This is just a very simple circuit. We already get this amount of errors. Imagine when we have a much larger circuit and we execute the circuit on the hardware, the results will be very messy and noisy. We cannot get any meaningful results. That's why we do not have practical quantum application yet. Because of these errors, it gives us the motivation to do quantum resource optimization. This figure shows the architecture of an IBM quantum hardware. You can see it only has like limited number of qubits. Each circle represents a qubit. And it has this nearest neighbor connectivity. It means that if we want to apply a CNOT gate between Q1 and Q4, it's actually we cannot do that because there is no direct link between Q1 and Q4. We need to insert like swap gates to create the connection between Q1 and Q4, and this is called the mapping overhead. We also have different error sources for the quantum hardware, like the single qubit gate error, the CNOT error rate, and also these blocks show the readout error of each qubit. It's important to note that each qubit has different error rate. Apart from that, we also have like decoherence error, crosstalk error, etc. Due to all these physical constraints of the hardware, we need to optimize the quantum resource to better utilize the near-term quantum hardware. So what are the quantum resources that we care about? For a quantum circuit, we will first translate it into a quantum circuit. For quantum algorithm, we will translate it into a quantum circuit, and then we execute the circuit on the quantum hardware. So in our project, our focus is at the circuit level. Here are some common metrics to characterize a quantum circuit, like the number of qubits, the number of single qubit gates. Oh, here we have 8 hardmark gates, and these dashed lines are just barriers to separate the single qubit gate and the 2 qubit gate. And then we have 3 CNOT gates, and the circuit depth is 5. These are the common metrics to characterize a quantum circuit, and we want to optimize these quantum resources. And to do that, we use the technique called mid-circuit measurement and reset. Oh, is there a question?
I have a question.
Yes.
Are these errors by the qubits, are they additive? Can they accumulate, or they cancel one another?
Sorry, can you repeat the question?
If the errors of 2 qubits, I can add the errors, or they cancel, the errors are canceled partially, or what's going on with, if I have so many qubits, hopefully in the future, so the errors may accumulate in an additive manner and overwhelm the system.
Yes. So the errors for now, they will be accumulated. So the results will be very messy. But if we achieve fault-tolerant quantum computing, it means that the errors won't be accumulated. And by then we don't need to worry about the errors. But for now, we need to care about errors.
So you will consider partial cancellation of errors?
Yes, now we try to use some error mitigation methods to try to cancel these errors.
Okay, thank you.
Mm-hmm. Are there other questions?
Yeah, I have one question.
Mm-hmm.
Just to maintain the superposition of qubit, we use that Hadamard gate. We apply the Hadamard gate, and then the qubit will come on superposition state. Yeah.
Yes.
And in currently there is a problem in coherence time. Yes, we have to maintain the coherence time also. So we want trying to make the coherence time a little bit longer. Yeah. So if qubit will lose the superposition state, then we want to take a proper state on a qubit. Yeah, that's our main goal. And if qubits lose the superposition state, then why we cannot use the again the Hadamard gate like in step by step? If we use that more Hadamard gate, then is there any problem in our output results? So or what sort of things will going on? Can you explain a little bit about me, that's not?
Yeah, the qubit will lose its information if we have.
The problem is that qubits was losing the superposition state, and we have to try to make the superposition state a longer time before the applying the another gates. Yeah.
Yeah.
Yeah, and then we are trying to solve the different materials also. We are trying to research on different materials also, in which materials we can just enhance the superposition states of the qubits. And so my question is that why we cannot apply the Hadamard? If some qubits lose the superposition state, then why again we cannot apply the Hadamard gate in every steps like that? My question is that. Question is that one. That is also one of the way to maintain the superposition states there. But why we need why we need the longer times to maintain the superposition of the qubits? Why we cannot apply the Hadamard gates at the time if it lose the superposition states?
Yes, I think when it loses information and then it goes back to state 0, and then
the process will also be reversible also. That's it. We have to be reversible also. Classical is not reversible. Yeah.
Yes, and then you can add Hadamard gate again. That's correct. But like for this example, but there are some other gates going on as well. So if you want to wait for the qubit to go back to the ground state and then you add Hadamard again, these other gates also, it's like resetting all the circuit, all the qubits. Then you can just redo another circuit. Otherwise, if you only care about one qubit, the other qubit will also lose its information.
And if I use the excessive number of Hadamard gates, then there will be a creation of a noise also. There is a problem of noise also there. If we use the if we increase the number of more gates, I think there is a problem of noise on circuit also. Yeah, I think that's one. Yeah.
Yes. Yeah.
Oh, I think that's the reasons. That's the reason. I got it. My answer. I'm just thinking. Okay, thank you.
Thanks. Okay. Now I will continue. So in our paper, we use the technique called mid-circuit measurement and reset. So previously, if we measure the qubit, we do not add other gates afterwards because there will be lots of errors and there are some hardware challenges to do that. But recently, due to some improvements on the hardware, now when we measure the qubit, we can put a reset operation to make the qubit go back to the ground state again and add some other gates afterwards. It is very important because it's a crucial part to do quantum error correction. So as I just pointed out, during this MMR, this Q1 should stay active, this is a long duration, so more decoherence error will be introduced. So in general, inserting MMR in the middle of a quantum circuit is a very challenging thing, but it's not the focus of our project, but I want to point it out. So, sorry, there is a question? Or
can you hear me?
Yes, yes, I can.
I have a question. You're talking about error correction. Don't we have intrinsic error? Do we compute with quantum physical states, and they all have a kind of Heisenberg Unschärfe, Heisenberg, how do you call the Heisenberg uncertainty principle?
Mm-hmm.
Because there should from the side of a physicist there should always be a kind of error in this computation.
Mm-hmm. Yes, I'm just trying to say that in error correction, because we need to detect the error in the middle, so we need this mid-circuit measurement. But yeah, that's for error correction. But now we use mid-circuit measurement to do circuit optimization, which I will explain it later.
On questions of errors, I wonder if there are different architectures of quantum systems. So I wonder if the accumulation of errors are the same on different architectures, or there are some architectures will tend to produce less errors.
Yes, the errors are different in different quantum hardware. And also the architecture is different. For example, for IBM quantum hardware, the architecture is this nearest neighbor connectivity. But for like trapped ion device, it's all-to-all connectivity. So the architecture is different.
So it means that the solution that you're trying to develop in terms of algorithms is then specific to a particular architecture, or are they general solutions applicable to all different architectures?
Okay. For the technique that I will introduce is general to all the quantum architectures.
Thank you.
Okay. So I will continue if there are no more questions. Now let me continue. We use MMR for circuit optimization, and here is a toy example to show how we do that. Initially, we have a small 3-qubit circuit, but after inserting MMR, we can only use 2-qubit circuit to represent the original 3-qubit circuit. And let me explain how we do that. It is based on the gate dependency graph. Here, each circle represents a qubit because we have 3 qubits. First, we apply a CNOT gate between Q0 and Q2, as shown in this green circle. And then we apply CNOT between Q1 and Q2, which is shown in this purple circle. We can see the end of Q0 only depends on Q0 and Q2. It is independent to Q1, but the end of Q1 and Q2 depend on all the 3 qubits. Since Q0 is irrelevant to Q1, we can insert the CNOT between Q0 and Q2. We measure it, reset Q0 to state 0, and reuse Q0 for Q1. In this way, we can only use 2 qubits to represent the original 3-qubit circuit. But not all the circuits are resizable. Here's an example. This figure shows the gate dependency graph of this quantum circuit. We can see the end of each qubit depend on all the 3 qubits. So there is no independent relationships between the qubits, so we cannot resize the circuit based on the gate dependency graph. So these are just some toy examples, but in reality, the quantum circuit are more complicated and it has many resizable opportunities. So in that, we need to design some algorithms to better resize the quantum circuit. So first, let me explain our gate dependency-based resizing algorithm. We have our input circuit. It has a bunch of resizable pairs. For each pair, it means we can reuse the first qubit for the second qubit. And to choose the resizable pair to insert, we define 2 cost functions. One is to maximize the qubit reuse. And the second one is to reuse some qubits, but we want to keep the circuit depth short because longer depth introduce more decoherence error. And we let the user to choose the cost function. We define 2 resizing algorithms. The first one is to enumerate all the resized circuits, and we pick the best one according to the cost function. But this one is very expensive if we have lots of resizable opportunities. The second one is to do local optimization using a greedy algorithm. Here, in this example, we choose the cost function to maximize qubit reuse, and we use this greedy algorithm for demonstration. The first qubit pair is selected, so we want to reuse Q0 for Q4. Now we can see we reuse Q0 for Q4, and one MMR is inserted. The circuit is resized to 4 qubits. Then we update the list of the resizable pair of this 4-qubit circuit. Now we have 2 options, and the first one is selected. We can see now we only have 3 qubits in the circuit. And then we update the resizable pair again, and it becomes empty, which means the circuit is not resizable anymore. Now we want to say, what can we get from the circuit resizing algorithm? What's the benefits? So the direct benefit is that when we execute the resized circuit on the quantum hardware, the fidelity of the circuit will be improved. So let's say we want to execute this circuit, 5-qubit circuit on this 5-qubit quantum hardware. At the beginning, we need all the 5 qubits, but in the end, we only need 3 qubits. Since each qubit has different error rate, we can pick the qubits with higher fidelity. And also, for the second reason, it is specifically for this IBM nearest neighbor architecture. If we execute this circuit on this architecture, because of this nearest neighbor connectivity, we need to insert some swap gates to make sure all the 2-qubit gates satisfy this connectivity constraint. And this is called the mapping overhead. If we have smaller number of qubits, we can reduce this mapping overhead. We can see the circuit, but you might observe that the circuit depth is growth from 2 to 6, which is not satisfactory because longer circuit depth will introduce more decoherence error. But after this mapping process, actually the depth of the first circuit is 6 and the depth for the second one is 8. So there is just a slight growth on the circuit depth. But overall, when we execute the smaller circuit on the quantum hardware, the fidelity will be improved. And that's the details about our gate dependency-based resizing algorithm. As I mentioned before, some circuits are not resizable based on the gate dependency graph. Can we make them resizable? The answer is yes, but under some certain constraints. So this circuit is not resizable based on the gate dependency graph. Before I explain how we make it resizable, I want to highlight that since each gate is like a unitary matrix, the overall performance of the circuit is like a big unitary matrix. So we can change the structure of the circuit arbitrarily as long as we keep the same unitary matrix. Here, these 3 circuits look different, but actually they are the same because they have the same unitary matrix. Now the idea is that maybe we can modify the structure of the circuit to make it resizable. First, we need to check if it is possible to do that. So we create a circuit in this structure. It contains 2 gates UA alpha 1 and UB alpha 2. The unitary matrix of this circuit can be represented with parameters alpha 1 and alpha 2. Then we use instantiation to optimize the parameters to make U2 approximate U1. If we can find such parameters, it means that we can reuse Q0 for Q3 by inserting this circuit measurement and reset, because Q0 does not interact with Q3 in this structure. Otherwise, if we cannot find such parameters, it means that we can never modify the structure of the circuit to reuse Q0 for Q3. So now let me explain what is circuit instantiation. For parameterized quantum circuit, we want to optimize the parameters to minimize the cost function. And here in this example, the target is a unitary matrix. So we want to optimize the parameters to approximate this unitary matrix as close as possible. And this is the cost function to do that. Now suppose we already found the parameters alpha 1 and alpha 2 such that U2 is approximately the same as U1. Here comes another challenge. We cannot execute this circuit U2 on the hardware directly because the hardware only accepts circuits that is composed of the native gate sets. The hardware native gate sets are some 2-qubit gates and single-qubit gates. So we need to decompose the two unitaries UA alpha 1 and UB alpha 2 to the hardware native gate sets. This process is called unitary synthesis. Then we get this new circuit U3. It is executable on the quantum hardware now. Now the challenge becomes, how do we do this unitary synthesis? We built our method on the top of a state-of-the-art called QSearch. It is a bottom-up synthesis algorithm to produce optimal circuits. And this figure shows the framework of QSearch. It starts with a layer of U3 gates, and then we add other layers. Each layer is composed of a 2-qubit gate and 2 U3 gates. We only add the layers to the coupled 2 qubits, which means that the output circuit will comply with the hardware topology directly, and we do not need to have any mapping overhead. So we use instantiation to optimize the parameters, and we iteratively add other layers. And then we use heuristic search algorithm to pick the best circuit that approximate the target unitary matrix with the least number of 2-qubit gate. In our paper, we developed this 2-block simultaneous unitary synthesis algorithm. First, we tried to use QSearch to synthesize the 2 blocks independently, but the results are pretty bad. We get very deep circuits with a large number of 2-qubit gates. Then we try to synthesize these 2 blocks at the same time. In this example, the target topology is this T topology because it has the shape of T. We add layer to the 2 blocks at the same time. For the first block, the layer can be applied between Q0 and Q1 or between Q1 and Q2. For the second block, the layer can be added between Q1 and Q2 or Q1 and Q3. So we have overall 4 possibilities. And then we use instantiation to optimize the parameters. And we add other layers and repeat the process until we can find a circuit that approximates the target unitary matrix. And these are the details about our instantiation-based resizing algorithm. And our resizing algorithms are built on the top of BQSKit. It is a software developed by our group at LBL for circuit optimization. We compare our resizing algorithms with BQSKit, TKit, and the vanilla version of BQSKit. We choose a bunch of quantum algorithms as the benchmarks, and we evaluated them on 2 different IBM quantum computers. Also, our code is now available on GitHub. Don't hesitate to try it out. Here are the results of our gate dependency resizing algorithm. The x-axis are some benchmarks, and the y-axis is the qubit count. The lower is the better. Compared with the non-resized circuit, our resizing algorithm can reduce the qubit count by 61%. And in terms of number of CNOS, we also can reduce it by 11%. And here are the results of our instantiation-based resizing algorithm. So the y-axis becomes qubit count again. Compared with BQSKit, our resizing algorithm can reduce the qubit count by 20%. In terms of the number of CNOT gates, we try 2 different topologies. One is T topology, and the other one is linear topology. We can see the number of CNOT gate is reduced for both topologies. Here are the hardware results. The y-axis is the fidelity of the circuit when executed on the quantum hardware, and the higher is the better. we can see the fidelity is improved for the two topologies. And I want to mention that all these circuits are not resizable for all the other resizing algorithms, including our graph dependency-based resizing algorithm. And we are the first one to make them resizable using instantiation. Here to conclude, here are some takeaway messages. First, our quantum circuit resizing can reduce both qubit and gate count so that the quantum resources is optimized. And because of that, we can improve the circuit fidelity, and all of them are achieved by inserting mid-circuit measurement and reset. Second, our instantiation-based resizing algorithm can find new resizable opportunities compared with the other resizing algorithms. For the future works, first we want to incorporate the hardware noise into the resizing process to further improve the circuit fidelity. And second, we want to scale the instantiation-based resizing algorithm to larger quantum circuits. And finally, since the mid-circuit measurement is related to error correction, we want to somehow combine the circuit resizing with error correction. And this is the link for our paper, and it will be presented in the DAC conference this year. So these are so now I will move to the second part. Oh, I want to give credits to my collaborators at LBL and UC Berkeley. So now I will move to the second part. So let me know if you have some questions. Yeah, please.
Yes, actually, there's a question from Cheng. Could you please explain a bit more on slide 34 on the equivalence between all three circuits?
Yes. So the circuit can be regarded as a unitary matrix. So if we multiply all these CNOT gates, they have the same unitary matrix, so they're actually the same. It means that for a quantum circuit, keeping the same unitary matrix, you have many different ways to implement a circuit. I hope this answers your question.
I have one question, okay?
Mhm.
While we take the qubits, we use the two-level system, yeah?
Yeah.
Two-level system, yeah. So why we cannot take more than two-level systems? What is the mandatory that we have to take two-level systems, like for a while we choose the qubits over there? Can you tell me?
Yes, so actually we are not limited to the 2-qubit system. We can definitely take 3-qubit system or more dimension. Like we have like Q-treats or Q-dits, which corresponds to 3-level system or 4-level system. But the problem is that like Q-treats, there will be more errors if we use the 3-level system. But if you can deal with the errors, I mean in the hardware level, if you can deal with the errors, of course you can use Q-treats to do computation, and there are many research works on that.
Okay, thank you.
Mm.
You can go ahead.
Okay. For the second part, I will talk about my recent work on using multi-qubit dynamical decoupling for crosstalk suppression. And this is the outline of this part of the talk. Since this project is mainly to deal with errors, first I will give a brief overview of some error mitigation or error suppression methods. And my focus is on dynamical decoupling, so I will give an introduction on dynamical decoupling and present more details of our proposed staggered DD protocol.
Hello?
Sorry?
Hello, I wonder if I can ask a question on the first part.
Yes, sure.
Yeah, in neural networks, there is a lot of discussion about the depths and the widths of the neuron, and you also had depths in your, or widths in your description of the circuits. The question would be, what's the trade-off and how we make a decision about the depths and the widths of the circuit or the gates?
Yes, that's a good question. So there are some trade-offs, because if we use lots of, maybe I can use this as a, yeah. If we use many mid-circuit measurements, then the circuit width, which means the number of qubits, is reduced, but we have the potential of increase the circuit depth. So there is a trade-off.
Okay,
Yeah.
maybe I'll try another question.
Mhm.
I know that there is a principle of no cloning.
Mhm.
Now, what could be the temptation to do some cloning here and to improve the efficiency, although there is a principle of no cloning, but maybe there are some opportunities to somehow do copying or cloning. So I may be confusing and confused.
Okay. Yeah, I don't think we can do any cloning here. So
Okay, we can
yeah.
ignore that. Okay,
Oh,
very
okay.
good. Thank
Okay.
you.
Thank you for your question.
Sure.
Yeah, and I will show some results of two experimental settings. One is idle experiment, and the other one is driven idle experiment. And finally, I will conclude and discuss the future works. Is there a question?
Yes, Frank has a question. I appreciate your work very much. However, I have a question. For each step of reduction, your steps of measuring of a quantum state, this is a reduction of information, and despite which QM school you follow, this is a kind of collapse of the wave function. Do you try what happens with your reduction approach with optimizing algorithm like QAOA? This depends on full quantum uncertainty during the complete algorithm processing. It's on the chat.
Yeah, that's a good question. And I will explain it with this example. Maybe, yeah, this one. So here we assume, after we have this CNOT gate, this Q0 does not have any information going on anymore. So when we measure it, and we do not lose any information, and then we reset it to state 0, so it will state 0, and then we add another gate between Q1 and Q2. So in this case, we do not have any loss of information. But if Q1 has some entanglement with the other qubits, then we will not be able to do that based on this gate dependency graph. But as long as it satisfies this gate dependency graph, we find these independent relationships between the qubits, then we can use this method without losing the information. And I remember there is a second part of the question, right?
Yes, I asked about here in the Q0, it isn't needed anymore. But if you have a chain of blocks, this kind of collapse of the quantum function that's in the mind of the people and using quantum physics, isn't this a problem when you make measurements between a line of quantum of qubits?
Yeah, because this one only works for a certain types of circuits. It does not work on all the circuits. So if it will, for that case that you mentioned, if it will cause some problems, then we just cannot resize this circuit.
Okay.
And I also remember you asked something about QAOA. So if QAOA is applied to a linear graph, and let's say we only have one layer of QA08, then we can resize the circuit. But if we have multiple layers, then we cannot resize the circuit.
Okay, I understand. Thank you.
I have a question.
Yes.
Yeah, my question is not really related to what you are teaching today, but it's more, it's on superposition. I had a conversation with a friend, a discussion with a friend about superposition of qubits, and I was arguing that when like a qubit can be in one state or another state, or on the superposition of two states. For example, when we talk about a cat is dead or is not dead, or the cat is at the same times dead and not dead. So how do we explain that in quantum computing or in quantum physics?
So before we measure the qubit, it is in a superposition. And but after the measurement, the superposition will be collapsed. And so it's like you mentioned the example, the cat is dead or alive. You don't know the answer until you check it. When you check it, then you just have one answer. It's counterintuitive, but that's how we explain it.
And so before you measure the qubit, so are we still using probabilities when you say that the cat is dead or not dead? Or when we talk about superposition, is it the moment where we talk about probabilities?
Yes.
Or we talked about probability after doing a measurement?
So what we do is that we will measure the state a lot of times, and then we will get a probability. If we just measure it one time, we can only have one result. We cannot know this alpha and beta here. So what we do is that maybe we measure it 1,000 times. So maybe we have 500 times we get state 0 and 500 times we get state 1. And then we know that it's in a superposition.
So how about if we do the measurement multiple time, we get the same result? So what will be the decision?
So if we always get the same results, we can assume that it's not in the superposition state.
But I feel like there's a mystery when we talk about the superposition state. When an atom is at the superposition state, it looks like no one knows what is the exact state of the qubit. Is that correct?
Yeah.
It's a mystery. Thank you so much.
Thanks for the question. So I will shift the focus on the error mitigation. Here is a nice figure to explain the error mitigation techniques. So if we do not have any errors, we give an input quantum state and we get this error-free expectation value. But in reality, noise exists. So when we measure it, we get this noisy expectation value. For the error mitigation method, they follow this type of framework. For example, we have different methods to realize error mitigation. For example, we can prepare the initial states in different ways, or we change the gate implementations. we change the measurement operator, or we use some ancillary qubits. So what we usually do is that we prepare the circuit in a bunch of copies, and then we use some post-processing method to derive this error mitigated expectation value. It should be closer to the noise-free expectation value. Some examples are the zero noise extrapolation or probabilistic error cancellation. On the other side, we have error suppression method. It is different from error mitigation because we do not need to fit the modified circuits to a model to derive the error mitigated expectation value. What we do is that we transpile the circuit to a smarter one and use some physics to reduce the errors. For example, we have the Pauli twirling. What it does is to inject some single qubit Pauli operators to the circuits to twirl the coherent noise to stochastic noise. And then we execute multiple circuits, and the average result can reduce the coherent error. We also have dynamical decoupling. It mainly focuses on the decoherence error. So we insert some single qubit gates, which is a few like classical overhead. And the benefits that we can realize error mitigation, error suppression by just execute this one circuit. And this is the focus of our project, dynamical decoupling. It can suppress the decoherence error by reducing the interaction between the quantum system and the environment. Here is an example. We have a single qubit quantum system, and it goes through some idle period. Because the quantum system is an open system, during the idle period, there will be some interaction with the environment, so the system will lose its information. And by interaction, it can cause some energy loss. For example, the state can go from the excited state to the ground state, or the interaction can cause some loss of phase information. Instead of letting the quantum system going through the idle period and do nothing, we can insert DD sequence to this idle period. The DD sequence is usually composed of some single qubit gates, and the overall performance of the DD sequence is like an identity gate. It won't change the state of the quantum system. Here is an example of the X2 DD sequence. It can reduce this interaction by inserting these two X gates. And these are the example about inserting DD for a single quantum system. And here's another example of applying DD to a quantum circuit. We have a 3-qubit circuit when we want to execute it on the quantum. Yeah, there's a question.
Yeah. If you reduce the interaction over there between the QI system and surrounding entanglement, is there any effect on entanglement between the qubits over there? While you use the CNOT gates, we have to use the entanglement over there by using CNOT gates there. So is there any effect on? Have you seen any effects on that one? If you reduce that interactions between the system and surrounding environment like that, so at the time that the entanglement phenomena, is there any effect on entanglement or not between the qubits over there? We apply to make entanglement. We have to use CNOT gates between the qubits over there, and the qubits will be entangled to each other. But if you reduce the interactions, means that somewhere else there will be effect on interactions on entanglement phenomena also. My curiosity.
So the environment. So when we talk about the quantum circuit, we usually ignore the environment. So there will be some entanglement on the quantum circuit, like the example that I'm going to explain. And since there are some delay, it means that this qubit going through some idle period, we insert this X2 sequence to the idle period. It can reduce the interaction with the environment, but there will be entanglement on the quantum circuit.
Okay, thank you.
Here is a more theoretical explanation about how DD can suppress the decoherence error. This is the Hamiltonian of an open quantum system. It is composed of 3 parts. We have the system Hamiltonian, which is like the quantum circuit that we care about. We have the Bath Hamiltonian, which represents the environment. And then we have this system-Bath interaction, which is the unwanted term, and we want to cancel this part. Here is an example. For example, we only have a single qubit quantum system with like dephasing system and Bath coupling. So we have this tensor products between the Z term here. After inserting these 2 XGate, the interaction HSB will become the unitary to represent this Hamiltonian can become an identity by inserting this 2 XGate, so that this interaction will be suppressed and we can protect our quantum system. And in our project, our focus is on the crosstalk error because we want to demonstrate it on IBM quantum hardware. So now I will focus on different crosstalk types on IBM superconducting quantum device. It has 2 types of crosstalk. The first one is static crosstalk, which is always on between the coupled qubits. For example, between Q0 and Q1 or Q1 and Q3, etc. They have this static, always on ZZ crosstalk. And also we have this driven crosstalk. It only happens when we introduce a cross-resonance gate. The cross-resonance gate is the hardware, the IBM native 2-qubit gate. And they use this gate to implement the CNOT gate. When we insert like a CNOT gate, it will introduce the crosstalk on the spectator qubits. Here's an example. For example, we have this CNOT here. It will introduce the driven crosstalk on this qubit, spectator qubit pair, and vice versa. Crosstalk exists not only in IBM superconducting quantum device, but also in some other quantum platforms like trapped ions, neutral atoms, semiconductor qubits, etc. We need to, and it's one of the major error sources. We need to find ways to deal with this crosstalk error. So now the goal is to use dynamical decoupling to suppress the crosstalk. But the standard DD sequence cannot suppress ZZ crosstalk, and I will explain why. We have a 2-qubit quantum system, and it goes through some idle period of 2 tau. We insert DD sequences to the 2 qubits, and they are the same on the 2 qubits. First, we have a free evolution of tau over 2, and we insert the first X gate, and another free evolution of tau. We insert the second X gate, and finally, free evolution of tau over 2. That's the standard way to insert DD sequence. During the free evolution, the ZZ crosstalk will be introduced, and it is modeled by this RZZ gate. This theta is related to the duration of the free evolution and the ZZ rate between the 2 qubits. And this ZZ rate can be obtained by the hardware calibration data from IBM website. Since this XX commutes with ZZ, this ZZ crosstalk will be accumulated across time. So this standard DD sequence cannot suppress ZZ crosstalk. In our paper, we proposed this staggered DD protocol. So here for the first qubit, it has the same DD sequence as the first one, but for the second qubit, we change the location of the X2 X gate to make them staggered with the first one, so that the 2 X gate do not happen at the same time. Since this Xi and Ix does not the anti-commute with ZZ, so the ZZ crosstalk can be cancelled. Even though this staggered protocol looks quite simple, but it can effectively remove this ZZ crosstalk. Here I will show the noise simulation results to compare our staggered DD protocol with the standard DD protocol. We perform this T2 Ramsey experiment, and this is the circuit to do that. First, we apply a hard mark gate, and then it goes through some free evolution, and we have this RZ gate here, which represents the phase accumulation across this delay time. And then we apply hard mark again, we measure the qubit. In this experiment, we use this relaxation noise model, which considers the relaxation and dephasing noise. We did not introduce the single qubit gate error because our focus is on ZZ crosstalk, so we do not want to make the noise model complicated. Here are the results. The x-axis is the duration of the delay, and the y-axis is the probability of returning to the ground state. We can see because of this accumulated phase, there is an oscillation here, and the frequency represents the detuning frequency, which represents the difference between the driven frequency and the qubit resonant frequency. And also the amplitude is reduced because of the errors in the noise model. So then we inject ZZ crosstalk to this circuit, and then we insert the standard X2 sequence to the delay time. We can see the oscillation frequency becomes 91 kilohertz. It is different from the original detuning frequency because of this ZZ crosstalk. And then we insert ZZ crosstalk and our staggered DD sequence. We can see the oscillation frequency becomes 99 kilohertz, which is approximately the same as the original one. This example shows that our staggered X2 sequence can remove this ZZ crosstalk. And we want to test different DD sequences for our staggered DD protocol. We choose XY, X2, XY4, and XY8. We prepare them in different versions like standard DD sequence, staggered DD sequence, and the inverse of staggered DD sequence. Because the staggered DD sequence is asymmetric on the two qubits, we can just switch the positions. So we call it the inverse of the staggered DD. We also prepare the DD sequence in the PM version. So here XP means XP is the same as the normal X pulse, but for X minus, it means the amplitude is negative for this X pulse. So if there are some systematic errors, this XPXM can compensate these errors. Now we know we have a bunch of DD sequences to evaluate, and we need to choose what circuits that we want to insert these DD sequences. So we choose this randomized benchmarking circuits because it is a well-used circuit to benchmark the error rate of a quantum hardware. These are the structure of a RB circuit. It is composed of a bunch of Clifford sequences, like represented by C1, 2, 3 here. Since these Clifford sequences are very efficiently to compute, we can calculate the inverse of this Clifford sequence and measure the qubits. If there are no errors, the qubit should go back to its initial state, which is state 0, 0. So here are the results. The x-axis is the length, is the number of Clifford sequences, and the y-axis is the probability of returning to the state 0, 0. Because error exists, when we increase the number of Clifford sequences, the return probability will drop. According to this curve, we can derive the average 2-qubit gate error for a quantum hardware. So now we want to apply DD sequence to this circuit. So how do we do that? we first insert delay between each cleaver sequences, and the delay is represented by this 2 tau here. We then insert different DD sequences to this delay time. We can see we have this X2 PM, we have XP, XM here, and they are the same for the 2 qubits. And then we have X2 PM staggered. We can see we shift the location of the DD sequence on the second qubit to make them stagger with each other. And then we switch the position, and it is called the inverse of X2 staggered DD. And we performed 2 experimental settings. For the first one, we apply this randomized benchmarking to the 2 qubit pairs simultaneously. And since the 2 qubit pairs are in the idle period at the same time, we call it idle experiment. And these qubit pairs follow this topology here, and they are neighbor pairs. So the static ZZ crosstalk exists in these pairs. For the second experiment, we perform RB circuit on the first qubit pair. But for the second qubit pair, we insert this SU4 gates. SU4 gates are some random single and 2 qubit gates. Because of these 2 qubit gates, it continuously introduced driven crosstalk to the first qubit pair. So we call it driven idle experiment. Again, these qubits follow this topology, and the driven crosstalk is introduced from the second qubit pair to the first one. And also the static ZZ crosstalk exists. Yeah, please.
Chen has a question. I'm a bit confused with the math for the staggered stacking for ZZ crosstalk reduction on slide 61.
This one? So since this XX and ZZ, they commute, so we can see this, we can move this XX to the end, and then this theta will be accumulated. So this ZZ crosstalk will be accumulated across the time. I hope that answers your question. But this XI and IX does not commute with ZZ. So after this XI ZZ, after this XI ZZ XI, the ZZ, there will be a minus theta. So this theta will be canceled with each other and introduce this identity operator. So that's how ZZ crosstalk is canceled. So I will move forward. Okay, before we execute the circuits on IBM quantum device, we need to pay attention that there are different CNOT configurations on IBM quantum device. First, there are 2 types of CNOT gates on IBM quantum hardware. The first one is this echoed cross-resonance CNOT, and the second one is direct CNOT. Here are the pulse shapes of these 2 different CNOT gates. We can see for the ECR type of CNOT gate, it has 2 cross-resonance gate echo with each other because it can remove some error terms when we construct the Hamiltonian of this cross-resonance. For the direct CNOT gate, it only has 1 cross-resonance gate term, but it has the shorter duration for this gate. So there are 2 types of CNOT gate. Yeah, please.
Yeah, what is the condition that, which condition we use that direct CX gate and another equal cross resonance CX gate? What is the condition? In what is the situation? So we have to use, in which situation I have to use this direct CX gate, and in which situation I have to use ECR gates?
Yeah, that's a good question. So for IBM quantum device, it's their choice to define which the CNOT gate is a ECR or DCX type. So I guess there are some physics consideration, hardware considerations there, but we do not have the choice to define. I hope that answers your question.
Okay, thank you.
Okay. And also for IBM quantum hardware, it has the native CNOT gate. So when we have these two qubit pairs, the connected qubits from the two pairs can have 3 different connections. For example, these 2 qubits are control qubits, and this one is control and this one is target, or we have this target and target. So we need to consider all these CNOT configurations. Keeping that in mind, we choose a subset of 10 qubits from this 27 qubit IBM device. Each arrow represents the native CNOT direction, and the yellow link shows the ECR type of CNOT, and the purple link shows the direct CNOT. We set the number of Clifford sequence to 8 to guarantee the initial fidelity is relatively high, around 1 to 8. And then we insert delay between the Clifford sequence, and the delay grows from this number to this number. They look a little bit weird, but actually there are multiples of this sampling rate for the pulse waveform generator on IBM device. We can assume that the fidelity should start from a relatively high number, and then it will drop because we increase the length of the idle period. So more errors will be introduced. We insert DD sequence to this idle period, and then we check the return probability. To quantify the average fidelity across time, we use this metric, average fidelity. Here, the T represents the maximum idle period, and F0 represents the initial return probability. Here are the results for our idle experiment. Since we have around 20 DD sequences to evaluate, first I will show some results, on some variants of X2PM, including X2PM, staggered of X2PM, and the inverse of staggered X2PM. First, for the first figure, it shows the results for the isolated RB experiment for this qubit pair, and then we apply the RB sequence to the 2 qubit pairs simultaneously, and this is the result for the first qubit pair. Here we just choose 2 qubit pairs for demonstration, but you can find all the results in our paper. We can see this black, the x-axis or the delay time, and the y-axis is the return probability. So as expected, in this free evolution, the return probability will drop across time because of the errors. And all the DD sequences can improve this return probability. The X2PM stagger and inverse of X2PM stagger perform approximately the same, and both of them outperform the standard X2PM. And to quantify that, our staggered X2PM improves the average fidelity by 12 and 20% for this isolated RB and SRB experiment. So then here are some results for XY4PM and XY8PM. Again, all of these sequences outperform this free evolution, but the XY4 PM consistently outperform the XY8 sequences. Even though XY8 is supposed to reduce higher order of errors compared with XY4, but since XY8 contains a larger number of single qubit gates, and the single qubit gate is not perfect, the single qubit gate error will be accumulated, and this circuit might be sensitive to this type of error. So XY4 performs better than XY8. we observe some dropouts here for XY8 sequence, because XY8 performs better than for the low frequency noise. So there might be some some constructive inference for the high frequency errors happening here. And these dropouts actually also have been observed in many other papers.
Sorry to interrupt there. Could you explain the case where there is no error at all? What would be the curve on the plots there, on the curve? Would it be a straight line in terms of delay?
Right. If there is no error at all, then no matter how long the delay we introduced, it will have no impact. So the curve should be always 1. Because of the errors, it will drop.
So basically, despite all this work that you've done in terms of error corrections, there's still errors there in these computations.
Yes, and we are not doing any error correction now. We are doing, yeah. Right.
Yeah, I understand. That's fine. Thanks.
And since XY4 outperforms XY8, so for the driven idle experiment, I will only show the results for X2PM and XY4. And this figure shows again the isolated RB result, and this figure shows the result for RB and SU4 experiment. And again, our staggered X2PM improves the average fidelity by 12 and 8.5% for the 2 experiments. Yes, there is a question.
On which computer are they done, or are this presentation done on a simulation like QuizKit?
It's on IBM hardware. It's a 27-qubit hardware called IBM Carol.
Okay, thank you.
Okay, to conclude, the main message that I want to convey here is that our staggered DD protocol can reduce the ZZ crosstalk more efficiently compared with the standard DD protocol. And we have demonstrated it on 2 experimental settings, the idle experiment and driven idle experiment, because we want to show that our DD protocol can tackle both static ZZ crosstalk and driven ZZ crosstalk. And our method can be regarded as the entry point for designing DD sequence for large quantum systems. For the future works, first we want to apply the staggered DD protocol to more advanced DD sequences, such as UDD, concatenated DD, etc., because they have been proven to have better results. And we want to combine our staggered protocol with these DD sequences. Second, because the circuits that we use, they only have the unified idle time. If we have a large quantum system with non-unified idle time, we need to design a new DD scheduling method. And third, we want to incorporate the staggered DD into the error correction code. And because the DD is an error suppression method and is different from error correction, we want to combine them together. And finally, as we observed some dropouts in the hardware, so it means the hardware noise is very complicated. We need more analysis on the noise resources and devise more hardware-oriented DD strategy. And you can find our paper here. And I also want to thank my collaborators, my PhD advisor, and my mentor at IBM. Okay, thanks for your attention, and I'm happy to answer your questions. Or if you have any questions later or want to collaborate, just feel free to send me an email. Thank you.
So I just wonder, maybe because I'm from engineering background, we tend to do validation. So I just wonder, how your work was validated. I was looking, basically seeing some quantum computation where you show there is no attempt for error correction first. and then same calculation, repeated calculation with correction, so that we can see the difference. So I was looking to see plots there of energy loss or phase loss without correction, and then with correction, so we can see the actual improvements.
Mhm.
Experimentally, that's what I was looking for. Do you have those kind of plots?
So for validation, I think what you mean that we should know the ideal results and then we show the improvements, right?
Yeah, that's correct.
Yeah, like for this one, we know that the correct result should be 1, and then without a DD sequence, this is the result. But after DD sequence, these are the results. So even though we do not convert it to the ideal result, but then there are some improvements. That's what we are trying to say.
Yeah, that's fine, but I still far away. You know, when I look at that, particularly for the delay, long delay, it means that we still have a significant error there of 30%.
Yeah, yes, right.
Yeah, it's fine. Yeah, thanks.
Thanks.
Yeah, I have one question. Okay, then. Yeah, is there any possibility, or are you working on that in topological materials? Because currently I'm working on topology files also. So is there any possibility like in error corrections, like in topological materials, topological quantum computing here? Is there anything else?
Yeah, maybe, but I'm not very familiar with that. So sorry, I cannot comment on that.
Oh, okay, thank you.
I have a curiosity question. Hello?
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 Hello, can you hear me?
Yeah, I have a curiosity question.
Mhm.
Do you expect or speculate the next breakthrough will come from superconducting or from photonics?
That's a very good question, but I think everyone want to know the answer, right? I'm not sure actually, but apart from superconducting and photonics, also like trapped ions and neutron atoms have very good results. So
Very promising. Yeah,
yeah,
with Xanadu, yeah.
yes, right. So I'm not sure, yeah, but we will see.
On the same question,
I must say that I love them all. All
Mhm.
those techniques are fantastic, fascinating.
Yeah, yes.
I thought on the same question as my colleague there. I thought that photonics, they tend to produce less errors and also operate at room temperature compared to the ion trap and superconduction, which require cooling.
That's right. Yeah, the cold atoms are complicated.
But the
They're very costly.
But the photonic device has the problem of photon loss, right? I guess, yeah.
Yeah, exactly. Okay, congratulations to everybody. You're working in a fascinating field.
Yeah, we are working very, very fascinating field.
In your opinion, I would like to ask you, at this current stage of the art, what would be the best application of the IBM computer, for instance, IBM quantum computer? Because as I look at it, we still have 30% error. For engineering, sometimes we're looking for almost exact solutions, and the DC doesn't give us exact solution. So what kind of application that you'd see for the current level of development?
Maybe we can do some quantum simulation for some quantum systems, that will be a very natural application. But as you said, there are lots of errors. So on the IBM side, they're exploring heavily on the error mitigation techniques, and it can make a big difference. Here, I'm just showing the results of dynamical decoupling, but as I shown before, there are many other error mitigation or suppression methods, and we can combine them, and then the results will be better than just using one error mitigation method.
Basically, you're saying that the current situation, we can only do computation for kind of qualitative assessment rather than quantitative. Qualitative, for instance, in terms of optimization, when we do optimization, so we may not require a quantitative I mean exact solution, but a kind of comparative kind of solutions that will give us the best solution in a comparative way. Is it the case?
Mm-hmm. Yes, and when we do optimization, it's very difficult to. Now we cannot approve that on the hardware results. The quantum algorithms can outperform the classical ones.
Yeah, fine, thank you.
Being as a postdoc researcher, what will be your suggestion for me? I'm a MSc physics student here currently. And what will be a suggestion for me? I want to be pursue my PhD on quantum information science. So what will you give me suggestion for me? If being as a postdoc researcher for you, what will be your suggestion for me?
So if you want to do a PhD in quantum computing?
Yeah, exactly. Yeah. That's why I'm here.
Okay. Are you applying for some PhD programs?
Yeah, I'm studying now 3rd semester. Yeah, I think, and then after I completion my, and I've done so many things on quantum computing, so many courses like that. But I want to enhance my skills, and I'm working on my skills also. So many research papers I study on. Even I am doing my thesis or also related to quantum computing. So what will be your suggestion for me?
Okay, yeah, for example, yeah, I think you've already done lots of things because you attend talks, and I guess you can, yeah, I assume you already read some books and follow some tutorials, and also like BQSKit, they have good tutorials. Also, you can read some papers, and many people, they open source their code, and I think you can start to learn from there, and maybe you can like do some projects or publish paper on quantum computing. It will be helpful for your application, I guess.
Okay.
Yeah, but yeah, it's already very good. When I apply for my PhD, actually, I do not have experience in quantum computing. I think
but you are being like quantum physicist. You are working on quantum computing now. That's good.
Yeah, yes. So yeah,
that's good.
Are there any questions?
You started from 1st semester, or you just took 2 years you took a course, and then later on after your performance you enroll into the quantum computing?
So I did my graduate school in France, and it's different from the US. I did my master for electronics engineering. Actually, it does not relevant to quantum computing. So, but after that, I switched to quantum computing for my PhD.
Okay, thank you. There is no more questions. All of were satisfied on your this presentation.
I have one last quick question. So someone brought up earlier about looking for the exact solution, and in terms of for the optimization here, and this is mathematically speaking, aren't we dealing with approximation and not introducing and searching for the exact solution in certain instances here because of the computationally expensive nature of that. And doesn't that introduce errors into the system as well?
Yes, yes, we have this type of errors, and the answer is it also introduced the errors on the system.
And is there any mitigation or correction happening for that, the introduced errors because of the algorithms or the approximation of what's being done? Or is that just something to be aware of, or it's a ratio of we know it's going to introduce this, or how is it being addressed basically?
Yes, I will talk about the one that I'm more familiar with is QAOA for solving the combinatorial optimization problem. For that one, it has been proven that if you increase the number of layers for QAOA, then the approximation ratio will be improved. So that's one solution to deal with this type of errors.
Gotcha. Thank you.
I think there is no more question.
Let me stop share my screen.
So do you guys have more questions?
I would like to thank Mrs. Yuan for a good talk. Thank you.
Thank you. Thanks for all the questions.
Yeah, you have given so nice presentation.
Thank you.
Just to say thank you too, and best wish for the future. We have lots of expectation from you from now on.
Yeah, I hope you will give some presentation in future also.
Okay, I will love to do that.
If it is possible for you.
Yes, sure.
Yeah. And then we can understand so many things from you, and then maybe there is some misconception on our in our quantum computing field. And then you will remove our misconception.
Thank you.
Currently, we are working mostly in superconducting qubits. Yeah, superconducting photonics. These two field are a little bit more active on quantum computing, as compared to other stuffs like topology. Quantum computing is, I think, this is a concept. I think that one.
Yeah.
If superconductivity was possible in room temperature, I think it will change the whole world.
Oh yes.
High temperature superconductivity, if you are able to resolve the path problem, then our complete physics will be completely different. Then
yes,
we will be
totally.
humanity will be next level. Our technology will be next level, everything, and we'll save our power, our power also. Yeah, because a lot of stuff our power was consuming in resistance like that, and we are wasting our energy now. And then it will save our energy, and we can utilize it other stuff also. So we'll be in next level, and then we can, I think we'll be in multi-planetary species also. Do you have any idea on BQE algorithms? BQE, like minimum energy estimations. Like I was trying to estimate the minimum energy of hydrogen atom, like by using quantum computing. That IBM, I have a lot of the simulator using that on stuff, programming stuff. I was doing on that stuff there. So is it for higher molecules current time? Is it not possible because of number of qubits? We have limited, but there is also error also. We don't have to just, because calculation is also not only one task. We have to focus on accuracy also, that one. So hydrogen one, I tried that one, and based on BQ algorithms, So it's working properly. But I was trying to attempt try to do in higher molecules, but it's not working.
Yeah, yes. I also only tried BQE on very simple stuff. What I do is just try to optimize the circuits for BQE, not to go to details about the algorithm itself.
Yeah. That's why we have to work on hardware parses. So that's why you can make more simulation. Exactly, that's one in more gables. For conducting qubits, like there are the particular position, the electrons there, we are using that like that. What sort of things? I don't know, because I haven't seen that. I was not in lab like that. I was seeing in like in this presentations like that. So what will be like the microwave pulses will go over there, and there is a place of electron exactly. It will be like still like also classical particles like that.
Yeah, it's very complicated apparently for the hardware side. And
How do you? Okay, thank you.
Yeah, what's your question?
So do anyone have more questions for Dr. Liu? Yeah, we got a good feedback. Thank you so much for the beautiful presentation. Yeah, we got a lot of good feedbacks.
Thank you. Thanks for you guys to attending.
Yeah, thank you for coming. And we'll have the next one about quantum chemistry. It'll be next week, June 15th at noon Eastern Time. So thank you all of you for coming.
Okay, thank you. Well, we next time also I'll come over here.
Well, next time I have a graduation, I will not be able to come. Can you send me the YouTube video?
Oh, sure. It's available on O1X.Let's YouTube channel.
And the slide as well?
Yeah, sure. No problem. Yeah.
I have a question to Team Orion. Is it possible to make a kind of after talk after some of your organized talks, after talk session?
Yes, we can make this one as an after talk session. So the talk is done, we can do a Q&A. Yeah, I reserve the Zoom for 3 hours usually.
Okay, we can see is the inside here is the offer, or it didn't quite understand you. You say after talk we could do it right here now.
So we can usually do Q&A after the presentation. So you should stay with this Zoom
Yes,
for 3
I'll stay
hours.
here. Okay, great.
But unfortunately, we don't have any Discord. So people can discuss on Discord, but we don't have that.
No, I wanted to say there are several sessions on Meetup or whatever, and afterwards there are some after talks, some other after talk discussions afterwards with the speaker and things like that. That's not part of the regular talk. As a suggestion for the future.
Oh yeah, yes, we can always stay. I can keep the Zoom up after the talk, so you guys can discuss afterwards.
Okay, that would be nice. Thank you.
Yes, just like today. It is so-called office hours. Dr. Liu, we have a question. Can you send me your slides so that I can forward to the participants upon request?
Sure.
Thank you. So if anyone don't have any question, we can call off this meeting. Thank you for
From
coming.
from where do we get the slides? That one. I also need the slides.
Yes, you can email me. Let me put my email on
Okay,
the
just
chat. So you can email me and
okay,
I will send you the slides.
I have a couple questions for Dr. Alan.
Sure.
Yeah, is it hard to find a job at IBM? So what tips can you give someone who has a master's degree in computer science to work on quantum computing?
So you're looking for jobs at IBM?
Yes.
You can check out their career website, I think.
Yeah, the problem I can check, but if you don't have it, tips how to present your resume. I already applied. My application was rejected. So I'd like to know someone, to be in touch with someone who is already there, so that he can give me like advice how to present my resume, stuff like that, so that I can know what I did wrong.
My experience is that I have a very high limit. They want to have PhDs after their doctor thesis. That's my impression here in Germany.
Oh, okay.
Don't want to encourage you, but it's not easy.
Oh, okay.
So if anyone don't have any questions, let's call off the meeting so we don't want to waste everybody's time. So thank you all for coming.
Okay, thank you. Thank you.